Hi everyone. This day we will discuss one of the applications of differential equations. And we will first take up what we call Newton's law of cooling. Newton's law of cooling states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. This is very observable in nature. For instance, if you have a cup of water here, and you will place ice cubes, the ice cubes will melt faster if the difference in temperature between the ice cube and the water is greater. If you place cold water, the ice cube will melt a little bit slower, whereas if you place hot water, that is the difference between the temperature of the water and the ice cube is great, then the rate of heat loss from the ice cube, or that is the rate of the change in temperature of the ice cube, is much faster, because Newton's law of cooling states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. That is, to state it another way, the rate of change of the temperature of a body, for instance, the ice cube, is directly proportional to the difference in the temperatures between the body and its surroundings. All right. So, if we have, if we let, for example, the temperature of the body as T, and A is the temperature of the surrounding or the atmosphere. Sometimes it's labeled as T sub S in some examples. And K is the proportionality constant, and T is the time, the smaller T is the time. Then Newton's law of cooling can be stated as the rate of change of the temperature, that is dt, delta T, but dt, because the rate of change sometimes is infinitesimally small, that is the rate of change, this is the rate of change of the temperature of the body, is directly proportional to the difference in temperature of the body and the surrounding or the atmosphere. So we write the proportionality constant K, and then the difference between the temperature of the body and the atmosphere, or T minus A. So after this, after we have formulated the equation, that is the rate of change of the temperature of the body is directly proportional with the proportionality constant to the difference in temperature of the body and the atmosphere or the surrounding, we can now derive the equation for the Newton's law of cooling using what we have learned in differential equations, that is separation of variables. So here we separate the variables, that is every term which has t in it will be on the left side with the dt, so that is t minus a equals k dt. Okay. And then, so we have now separated the variables. What is the next step? The next step is integration or anti-differentiation. So we integrate, and then the derivative of dt over t minus a is, of course, we know it is ln of t minus a. Okay, and the derivative of the integral of k dt is simply equal to, since k is a constant, we take it out. Sorry. So since k is a constant, we can take it out of the integral sign, and then we integrate dt. The integral of dt is simply t, kt plus c. But instead of writing c, we write ln of c. Okay, ln of c. so that we can simplify it better. Then we transpose ln of c to the other side of the equation, to the left side, so that all the logarithms are on the same side. So ln of t minus a absolute value minus ln of c equals kt. Now there is a rule in logarithm, as you have already known, that the difference between two logarithms is equivalent to ln of t minus a over c. So we can place them in terms of 1 ln, then this becomes kt. In order to remove the natural logarithm, we raise everything to e. We raise both sides to e. So e raised to the power of ln of t minus a over c equals e to the power of kt. Okay. Then this becomes t minus a over c equals e to the kt is still e to the kt, whereas on the left side the natural logarithm has been removed because of the presence of because it was raised to the base of the logarithm. And then this becomes t minus a equals transpose c to the other side. This becomes c e to the kt. Okay. Then transpose a to the other side in order to have t on the left side as the missing variable, as the one we are looking for. So a plus c e to the kt. Now this means that if we have the temperature of the surrounding, if we have we are going to look the temperature of the body at a specific time t, at any time t, we can already find that temperature, that missing temperature, if we only know these values. And so this is now what we call the formula for the Newton's law of cooling. Okay, this is the formula for the Newton's law of cooling. That is T equals A plus CE to the power of KT. That is, the temperature of the body, temperature T of the body, is equal to the sum of the temperature of the surrounding plus C e to the power of the proportionality constant K and time T. So let's say you give the temperature of the, let's say you have a thermometer and you brought it to a room where the temperature is A, and you find out after time, let's say after time equals 10 minutes, what is the temperature of the thermometer after it has been brought to the room. You can already solve it using this formula. Alright? Sometimes you can find in some resources that the C is already missing. That is because, let's say, if you are given the temperature of the body at time equals 0, let's say at time equals 0, the temperature of the body is equal to T sub O, then we can substitute it into the equation. So let's say at T equals 0, the temperature is T sub O. We can just substitute any temperature for that when we already have the problem, because it is almost all the time specified in the problem, unless it is the one we are looking for. It is the one missing. So if we have if for instance, at time equals 0, T is equal to T sub O, then we can substitute that into the main equation. T sub O is equal to, so the temperature of the body is T sub O, that is at A plus C e to the power of k times 0. K times 0. K times 0 is equal to 0, right? Okay. K times, but it was specified that the temperature of the body is 0. So K times 0 is 0. E raised to the 0 is 1 because any number raised to 0 is 1. So this becomes A plus C times 1 equals T sub O. So the temperature of the body when time is equal to 0 is T sub O. So that means C is equal to T sub O minus A. And so if we substitute this to the main equation above, the equation we have boxed, we can have T, at any time T, the temperature of the body is equal to the sum of the temperature of the environment or the surrounding plus C, where C is equal to T sub O minus A, T sub O minus A, then E to the power of K times T. Alright, so we can have this as our alternative equation. That is A plus T sub O minus A, okay, E to the power of KT. Sometimes it is written as T is equal to the temperature of the surrounding T sub S plus, okay, temperature of the body when time is equal to 0 minus T sub S, okay, E to the power of KT. So this is the alternative. This is the alternative equation to this equation. That is, you have already derived C when T is equal to 0. So we can say that this is the general solution of the equation. This is a little bit more particular, a solution that is more particular. Although we can still obtain K, the value of K, still using the process for obtaining particular solutions, but we can say that this is already a more particular solution. Alright, so you do not have to memorize anything. I do not memorize Newton's law of cooling when studying it or solving problems related to it. You simply have to understand the principle, and then from the main principle, from the principle of the Newton's law of cooling, you derive the equation using separation of variables. So that is the difference in temperature, right? The difference in temperature of the body, the rate of change of the temperature of the body, this is the rate of change of the temperature of the body, is directly proportional, right? K, proportionality constant, to the temperature of the body and the surrounding, the difference in the temperature of the body and the surrounding. Okay, so thank you everyone, and we will try to solve another video. We will try to solve in another video an example on Newton's law of cooling. Pasensyahan nyo lang ako nga agi. Wala ko sang pen to write. So anyway, thank you for your time and patience. God bless.